Hello, and welcome to a video on spring potential energy for grade 12 physics. When we compress a spring, Hooke's law gives us information about how much force is required to hold the spring at that compression or at that stretch. If I want to figure out what's going to happen when I release that spring and it pushes something, this gives us problems for our grade 11 physics formulas because the force changes as the spring expands or contracts. My force is no longer constant. In order to look at this, we need to figure out what's going to happen with the energy stored in the spring. So using the energy, I can use this to figure out stuff about, for example, how fast a projectile might be going. Let's take a look at an example here. So in this case, I've got a spring-loaded dart gun with a constant K that's used to shoot a dart with a mass M here, straight up into the air. And I've got a compression here, which is going to be X. I could figure this out from Hooke's law, the force that I would need, but I'm not looking for force here. I'm actually looking for a final velocity here. What's the velocity of the dart? So let's start writing out what I know here. I know that my spring constant is 2,000 newtons per meter. Be careful about your units here. This is newtons per meter. This is centimeters. So if I look at this, my mass is pretty easy. That's 0.20 kilograms. Those are my standard units. And my stretch is 10 centimeters, which works out to 0.10 meters. Make sure your units are correct here. I'm looking for what is my change in velocity here, or my final velocity, because it starts at 0. So let's work this out. Now, one thing to note, there is a new formula here for the potential energy stored in a spring. So the potential energy stored in a spring is 1/2 times the spring constant times the stretch or compression squared, 1/2 kx squared. That formula may look very familiar, and in fact, it is very familiar. This pattern of 1/2 something squared is something that shows up a lot in our formulas, and there's a really good reason for that, and that is calculus. So look forward to that when you're taking calculus. So in this case, we have our potential energy stored by the spring is 1/2 kx squared. Let's substitute things in. 1/2 2,000 0.1 squared. There we go. Working this out, my potential energy stored in the spring is a whole 10 joules. There we go. Now remember, when I'm looking at potential energy and how much that potential energy is stored, that potential energy can be turned into kinetic energy. So this here can become kinetic energy. This could be a bunch of other things. Eventually, this could be, depending on what process I go through, this could become potential energy due to gravity or a couple other things. But in this case, our problem is saying this becomes kinetic energy. Now, I do know the formula for kinetic energy. My formula for kinetic energy is 1/2 mv squared, 1/2 times mass times velocity squared. And if you look, notice this is the same pattern here. And there, again, there's a really good reason for that. So my kinetic energy is 1/2 times mass times velocity squared. Plugging things in. My kinetic energy, because my potential energy became my kinetic energy, is 10 joules. Equals 1/2. My mass is 0.2 v squared. And in this case, solving this out, don't forget to square root to get rid of this here. My final velocity is 10 meters per second. So there is my final velocity for this dart. So as I'm going through here, note that we have a new formula here Make sure that you write that down and note that you have K and X in here, your spring constant and your stretch. And this is potential energy due to or stored in a spring. And then this potential energy can become kinetic energy. There's a couple of different ways that a couple of different other types of energy we could look at. But in this question, because I have a velocity, when I have a velocity, I have a kinetic energy. So velocity is a good indication that you might be looking for kinetic energy with something. I hope this has been helpful. Take a look in the next video. We'll do another example of this.